Okay, so let's see a few examples. So here's a simple example, right? Cos theta 0 plus sin theta 1, examples of qubits. So this is easy that the normalization condition obviously holds here, right? In the previous slide we saw the 0.80 plus 0.61. This is something we saw in the last slide. I want to note here that actually I could change the plus to minus, right, and this would still be valid. Why? Because, well, 0.8 square plus minus 0.6 square actually still remains as 1, right. So even though the amplitude has actually changed, right, but it remains a valid qubit. And I want to sort of quickly make a note here that in fact the amplitude can be complex. Okay, so an example is psi equals to I 0 plus 0 1, or maybe 1 over root 2 I 0 plus 1 1, right. So in this case you will always find the qubit when you measure, you will always find it in state 0, right, because all the amplitude is over there. Okay. Here in the second one you can check that the normalization holds. So I over root 2 the whole squared plus 1 over root 2 the whole squared is nothing but half plus half, which is 1. Alright, good. So now that we've established a little bit of notation, we already saw previously that any two-state quantum system can be written as a linear combination of the basis states, and the basis that we have been using so far is this so-called standard basis, so 1 0 and 0 1. There is also another very popular basis which is called the Hadamard basis. So this is kind of cool because the basis is quantum, it has quantum behavior, right. So here the basis vectors are superpositions of classical bit vectors, right. So there is the plus the plus state, which is 1 over root 2 0 plus 1 over root 2 1, and the minus state, which is 1 over root 2 0 minus 1 over root 2 1, right. And you can verify for yourself that this is a valid basis. And as a simple exercise, you can try to represent the standard basis in terms of the Hadamard basis. So here we have expressed Hadamard in terms of standard. It's a nice exercise to do the opposite. Okay, so far we have talked about single qubits, but obviously to do anything useful with any bit, right, classical or quantum, you need more than one bit in general. So let's try to extend our discussion now to handle multiple qubits. So now say we have two qubits A and B, how should we write these? So any ideas? If I have these two qubits A and B, okay, so let me again set up some notation maybe over here. Okay, so let me say I have like psi A, sorry, I meant a different, yeah, and I have psi B. First of all, now I have two qubits. Can I still do this thing where I write it as a linear combination of some basis vectors? This is the first question, right? And the answer is yes, of course you can, but you need to extend your basis vectors to handle a larger dimension, and this is not hard to do, right? So what's the first idea that would come to you? So for the case of for the case of two 2 qubits, which is what we are looking at here, right. Obviously, maybe I'll erase this. Yeah. So obviously, the standard basis that pops out for us over here is this. Right. So, if I want to write this 2 qubit state as a linear combination of basis vectors, then the most natural thing for me to do is extend my basis vectors into, to handle this larger dimension, which is what I have done over here. And this is called the following. Okay, and now so now any 2 qubit state I can write as a linear combination of these. So what's a sort of very simple example, right? So if I have some psi AB, I can write it as a linear combination, and let's say the linear coefficients are half, right? So half 0 1 plus half 1 0 plus half 1 1. So once again you want this condition that the sum of squares of absolute values of these amplitudes should sum up to 1, and this is of course sort of satisfied here, right. So because I have half squared, right, maybe it's better to say 4 times half squared is what I have here, right. This sum is 4 times half squared. So summation x in 0 1 squared, right. If I write half squared, this becomes 4 times half squared, which is obviously 1. So this is valid. Okay, and you can generalize this to n qubits. So now instead of 2 to the 2, I'll have 2 to the n as the dimension of my basis vectors. And for simplicity, as I did before, I'm going to actually sort of let each basis vector correspond to this, this state of size d, right. So, for n qubits, I can have length n vectors, each of which length n strings, I should say, each of which corresponds to a basis vector of length 2 to the n. Okay, I hope that that's clear, right. So basically my x is of size n, right, but each string of length n is corresponding to this basis vector of length 2 to the n for orthonormality. And once you go into these multiple qubits, you encounter some very, very interesting phenomena such as entanglement. So, we will not talk of entanglement right away, but I do want to point out a very nice example of a multiple qubit, a 2 qubit state, which is the so called EPR state, right. So, this is Einstein, Podolsky and Rosen. This is a famous state named after these 3 famous scientists. This is 1 over root 2 0 0 plus 1 1. Okay. So, as I already said, we later show that this state is entangled. We will define it also later. So, now how do I combine qubits, right. So far here we have seen these multiple qubits, we have talked of these basis vectors. But now if I have 2 arbitrary qubits, right. So let us say psi A, which is this, and psi B, which is this, then how should I express their combined state? So it turns out that we express their combined state via the tensor product. Okay, so let me write down the combined state now of psi A and phi B. So this is going to be the tensor product of these two vectors, and this expands out as alpha A alpha B beta B and then beta A, you copy that and then you again write alpha B beta B. Oh, so I should emphasize that I made these boxes just to show you what sequence to follow. So it can be a little confusing because here I say alpha A, alpha B, beta B, but why don't I say alpha A, alpha B, beta A, alpha B? I mean, so I'm just writing these boxes, these boxes are not really there, right? So it's just alpha A, alpha B, beta B, beta A, alpha B and beta A, beta B. So it's just this, okay. Yeah, so this is the tensor product, and in terms of notation, okay, so just a quick note over here. In terms of notation, I won't always sort of write this longhand notation like this. I can get rid of this, and I can also get rid of this and this. So I can write it as this. I can also just write it like this. So this is just to make life easier for us. Okay, so a few simple exercises that you can try here. So establish that the tensor product is distributive and associative but not commutative. I am not going to do it. What I will do is something more fun, which is I am going to show you how the simple ideas that we have already studied allow us to do something very, very cool already. Yes, just in lecture 1, right? Previous one was lecture 0. So, I am a computer scientist, right. So, okay, so I am going to show you how to generate true randomness. Now, first let me show you what I mean and then we will talk about it. So, okay, what's my first step? So, first I am going to prepare a Hadamard state. Actually, I am going to use, let me stick to my color mnemonic over here. Yeah. So, I am going to prepare the Hadamard state. Okay, so this is a superposition of 0 and 1. And now what I am going to do is I am going to measure this state in the standard basis. So, this is something that I didn't as yet tell you about, right. So, I've been assuming that you always perform the measurement in the standard basis, but that is not true. I could perform the measurement in different bases. So, for instance, if I measure against a Hadamard basis like this same state here, if I measure it in the Hadamard basis, then with probability 1 I will get the plus state. But if I measure it in the standard basis, right. So, this is if I measure it with this basis, then what do I get? So, in general, as we see in this note, this bullet point here, if we want to measure any state psi in some orthonormal basis Bj, the probability of observing the outcome Bj is given by the inner product of Bj and psi, right, the mod squared of this, of Bj inner product psi. So, in particular, now what is going to happen when I measure this state in the standard basis? So, what is the probability that I get state 0? this is going to be by our by what we saw over here. It's going to be the inner product of 0 and plus, right, mod squared. So, this is 0, right, 0, this is what it is, right. And now because our basis is obviously orthonormal, right, what is inner product of 0 and 1? So, I hope that this is sort of immediately clear, but maybe I'll still write it, right. So, if I take this is what? This is 1 0, right, and this is 0 1, right. So, what is this? So, this is 0, right. So, it's just 1 0 0 1, right. So, this is 0. So, that is why it's it's the basis vectors have to be orthonormal. So, this thing goes away, right, and this on the other hand is simply 1. Again, you can just work it out. So, this, what do I get here, right? So, I get half, isn't it? So, what I get here is half. Okay, so this is very cool. Why? Because what did I do? I generated a random bit, and this is something which in the classical universe, I mean, we don't really have good ways to do, because yes, we talk about randomized computation, right? And what is randomized computation? What's a randomized algorithm? It's an algorithm where you have random bits for free, right? So, basically it's like the algorithm has a coin tosser sitting inside it, and this coin tosser tosses a coin, it gets a random bit, and then you use that randomness in your algorithm. But where is this randomness really coming from? It's not like our computers have these mechanical arms which are sitting and tossing coins, right? Just imagine what happens if you don't catch a coin that you tossed. Anyway, sorry for the bad joke, but where is this randomness coming from? So, in the classical world, we have to make do with fairly imperfect solutions. So, typically, our operating system has what's called a pseudo random number generator, which is just a piece of code that implements some kind of function which which gives you bits which you conjecture are random. There's actually a lot of theory behind this, but one of the things that we don't have there are truly random bits in constant supply, right. So, this is amazing. So, here using quantum computing, you're able to generate truly random bits. This is already something very useful and that we did not know how to do before. What's the catch? Actually, there's not much of a catch. Just that, well, you're moving into a model of computation which has built-in true randomness. So, the fact that you prepare the Hadamard state, you kind of inject the randomness and then you measure it and then you sort of get it back. So, all the magic is actually happening over here, right, in this preparation of the Hadamard state, right. So, how do we prepare this Hadamard state? I mean, this is something that we should think about, because otherwise we didn't do anything. Where it's like saying, well, I have a genie and then the genie gives me randomness for free. So, how do we prepare this? We'll see this in upcoming lectures. For the moment, we'll just say that we can do it, and this is a true statement. And when we do it, then we can get truly random bits. Okay, so to sum up, even though I have already talked about measurement in today's class, I will give you some notation for it. So, this is the notation. Okay, so this little box like this is our notation for measuring a qubit or a sequence of qubits. And as I already said multiple times, measurement of the quantum system collapses the wave function and results in the state being found in one of the basis states. As I already also said, but something that is really worth repeating, is that it is the only way in which you can access the output of any computation that you did. Okay, so in the quantum state, maybe you did some sort of exponential number of computations, but a measurement is the only way that you can access it. And when you measure, then as we just now said, I mean, you're going to find the state in one of the basis states, and the probability that you find it in one of the basis states is, you know, the mod amplitude squared, right? So in order to get anything really useful out of a quantum algorithm, it had better be the case that the amplitude is, you know, encoding some interesting information, right? So it should be the case that, you know, which basis state you got is encoding some useful information. We will see many examples of this as the course progresses. Okay, so yeah, so this is the notation of measurement. And another simple thing which is worth repeating is that yes, you know, when you measure the quantum state, then you get the some basis state with a certain probability which depends on the square of the 2 norm of the associated amplitude. So here we are being a little careful because the amplitude can be complex. Okay, but once you measured and you know, the wave function collapsed, right? You got one basis state. At this point, you can keep measuring as much as you want and you will keep getting the same result. Okay, so this is important to remember. So once you collapse the state, then you're kind of done. So now you no longer have the magic. Okay, so you just keep getting what you already got. Okay, so let me just end with some acknowledgements. So a lot of the slides that we use in this course are based on material that has been developed in courses offered at UIUC Princeton and also CMU. See web page. So, you know, I already updated that. And the images are, you know, courtesy Google Images that applies throughout the course. So, yeah, that's all I wanted to say for today. Thanks for your attention. Thank you.